Okay, guys, today I wanted to talk to you about something called Vesper, which is a theory that we use to help us explain molecular shapes. So, if you guys on the page that you're on, if you haven't already, this PhET is pretty cool. And what it's showing us is, the spheres are the atoms, the sticks are the electrons in the bond. So these would be single bonds. And you can see as I add more bonds that the electrons in the bonds kind of want to spread out. It's also possible to have electrons that are not in a bond, and those can cause kind of a distortion of the shape. So I will show you another one. So the way for these two atoms to get the furthest away from each other is for them to kind of be, to be in a 180 degree angle, which we call linear. And then if we add more, two, again, they're going to be linear. But if you add a lone pair of electrons, now you can see that the lone pair of electrons is very negative, which is causing repulsion of the bonds, which causes the angle to decrease and causes bending. This would be like what water molecule would look like with the two unbonded lone pairs. Oxygen would be the purple, and then the whites would be the hydrogens. So molecular shape, knowing the shape of a molecule is going to help us with understanding why certain molecules do what they do. And like I said before, the theory that we use is called Vesper. It stands for valence shell electron pair repulsion. So the letters in the description here really tell you what it is. So the valence shell electrons are going to be in pairs and they're going to repel each other. So now there's something called hybridization, and I'm going to show you an example here. I think is the most classic example. What happens when something is getting ready to bond is the electrons hybridize. So if you think about just a plain carbon atom over here, it would be 1s2, 2s2, 2p1. But when it's going to bond, these three orbitals become four, and they're equal in energy, and they're kind of in between, like a hybrid is in between the energy of the s and the p. And now the electrons can be one in each orbital. So this is why when we draw carbon, we draw it, with a dot structure. I always have taught you guys to start at 12 o'clock and go around. That's representing these four electrons. So that's why it can bond 4 times. If it didn't hybridize, it looks like it would only bond 2 times. But it does do this. And we call this sp3. You can think of like there being a little superscript 1 there. And that adds up then to 4 total hybrid orbitals that are between the s and the p in energy. So I'm going to have you guys fill out this sheet with me. And what it's showing us is a lot of different things. I'll just kind of explain it as we go. One is electron geometry. These are all tetrahedral, and that is because we're talking about this sp3. So again, think of there being a 1 there. There really isn't. So sp3 is going to add up then to a total of 4 orbitals. So these are all considered tetrahedral. So there is the classic tetrahedral shape. And I'll show that to you on the FET in just a minute, but let's just make sure we're good with terminology. There's something called ABE that we're going to be filling out. A is always referring to the central atom, and E is the